Somewhere in the universe, two black holes are spiraling toward each other. For millions of years they have circled in darkness, drawn together by gravity, their orbit tightening so slowly that entire civilizations could rise and fall between the smallest changes in their path. And then, in the final moments, they merge. In less than a second, more energy is released than all the stars in the observable universe produce combined. Not as light, not as heat, but as a ripple, a disturbance so fundamental that it does not travel through space. It travels as space itself, stretching and compressing the fabric of the universe as it moves outward in every direction at the speed of light. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Tonight, we are looking at gravitational waves. We will begin with the nature of space-time itself and work through how these waves form, how they travel, and how humanity built an instrument sensitive enough to detect a distortion smaller than a proton. We will follow the story of the first detection, explore what gravitational waves have already revealed about the universe, and look at the remarkable future that lies ahead for this new way of listening to the cosmos. Chapter 1. What is space-time? To understand gravitational waves, we first need to understand what they move through. And that means starting with something that seems almost too familiar to question: space and time. For most of human history, space was thought of as a kind of container, an empty stage on which the events of the universe played out. Stars burned in it, planets moved through it, but the stage itself was considered fixed and neutral, indifferent to whatever happened within it. Time was similarly straightforward, a river flowing in one direction at a constant rate, the same for everyone everywhere, ticking forward without variation. This picture made intuitive sense. It matched everyday experience, and for centuries it served science well enough. Then came Albert Einstein. In 1905, Einstein published his special theory of relativity, which introduced a deeply unsettling idea. Space and time are not separate things. They are two aspects of a single unified structure. What we experience as the passage of time and what we experience as the distance between objects are woven together into something physicists call space-time, a four-dimensional fabric in which 3 dimensions of space and 1 dimension of time are inseparable from one another. This was already a significant departure from common sense. But Einstein was not finished. 10 years later, in 1915, he published his general theory of relativity, and with it came an even more radical proposal. Space-time is not rigid. It is not fixed. It can bend. It can curve. And the thing that curves it is mass. Imagine placing a heavy object onto a stretched rubber sheet. The sheet dips and deforms around the object, creating a kind of well. Anything moving nearby will follow the curved surface rather than a straight line. This is, in simplified form, what mass does to space-time. The Earth curves the space-time around it. The Sun curves it more. A black hole curves it so severely that not even light can follow a path that leads away from it. What we call gravity in Einstein's framework is not a force being transmitted between objects in the way Newton described. It is the natural consequence of objects following the curves in space-time created by mass. The Earth does not pull the moon toward it with an invisible hand. The Earth shapes the space-time around it, and the moon follows that shape. The geometry of space itself guides the motion. This distinction matters because it changes what gravity fundamentally is. In Newton's picture, gravity is a force that acts instantly across any distance. In Einstein's picture, gravity is geometry. It is the shape of the universe itself, responding to the matter within it. And if gravity is geometry, then a change in that geometry, caused by matter moving or accelerating, must propagate outward through space-time the way a disturbance propagates through any medium. Not instantly, not invisibly, but as a wave. That is the foundation from which gravitational waves emerge, not as a separate phenomenon bolted onto general relativity, but as a natural and inevitable consequence of it. If space-time can curve, it can ripple. And if it can ripple, those ripples can travel. Before we follow that idea further, it is worth sitting with the picture for a moment. We are not talking about waves moving through space. We are talking about waves that are space. Expansions and contractions of the fabric of the universe itself, passing through everything, altering the distances between objects as they go, leaving the universe ever so slightly different in their wake. It is one of the stranger ideas in all of physics, and it turns out to be true. Chapter 2. Gravity as Geometry. We ended the last chapter with a picture of space-time as a fabric, one that can bend and curve in response to the presence of mass. Now we want to look more carefully at what that curvature actually means, and why it leads so naturally to the idea that disturbances in that curvature can travel outward like waves. Newton's description of gravity served science extraordinarily well for over 2 centuries. In his framework, every object with mass attracts every other object with mass, and the strength of that attraction depends on how massive the objects are and how far apart they sit. The formula is clean and precise. It predicted the motions of the planets with remarkable accuracy. It explained the tides. It allowed astronomers to calculate the existence of Neptune before anyone had ever seen it, simply by noticing that Uranus was not moving quite as expected. But Newton himself was troubled by one aspect of his own theory. Gravity, in his description, acted instantly across any distance. If the sun were to suddenly vanish, Earth would, according to Newton, immediately fly off in a straight line, with no delay at all. There was no mechanism for how the force was transmitted, no medium through which it moved. It simply acted everywhere at once with no explanation for how that was possible. Newton acknowledged this openly. He called it action at a distance, and he offered no hypothesis to explain it. It worked, but it left something important unanswered. Einstein's general relativity answered it, and in doing so, it replaced the entire concept of gravitational force with something geometrical. In general relativity, mass does not reach out and pull on other mass. Instead, mass tells space-time how to curve, and curved space-time tells mass how to move. The 2 parts of that sentence are equally important. It is a conversation between matter and geometry, each shaping the other continuously. The path that an object follows through space-time is called a geodesic. In flat space-time, with no mass nearby, a geodesic is a straight line. An object with no forces acting on it moves in a straight line through space at a constant speed. That is simply Newton's first law, expressed in relativistic terms. But near a massive object, space-time is curved, and the geodesics curve with it. An object following a geodesic near the Earth is not being pulled by a force. It is following the straightest possible path through a curved geometry. What looks like a curved trajectory through space is actually a straight path through curved space-time. This is a subtle but important distinction. The Moon is not being held in orbit by a gravitational rope connecting it to the Earth. The Moon is following the natural geometry of the space-time that the Earth has shaped around itself. Remove the Earth, and the geometry flattens, and the Moon travels in a straight line. Now consider what happens when that geometry changes. When a massive object moves, the curvature of space-time around it changes too. And those changes do not propagate instantly the way Newton's gravity did. They propagate at the speed of light. They spread outward from the source the way ripples spread across the surface of water when a stone is dropped into it. This is the origin of gravitational waves, not a separate prediction added to general relativity from the outside, but something that falls directly out of the theory's own logic. If space-time curvature is real, and if changes in that curvature travel at a finite speed, then gravitational waves must exist. The analogy to water is useful but imperfect. Water waves are oscillations of water molecules. Sound waves are oscillations of air pressure. Gravitational waves are oscillations of space-time itself. There is no medium they move through. They are the medium moving. As a gravitational wave passes through a region of space, distances in that region change. Objects that are separated along one axis are pushed slightly farther apart, while objects separated along the perpendicular axis are squeezed slightly closer together. Then the wave continues, and the pattern reverses. The effect alternates, stretching in one direction while compressing in another, over and over, as the wave passes through. The scale of this distortion is almost impossible to convey. For the strongest gravitational waves ever detected on Earth, the change in distance across a detector 4 kilometers long was roughly 1,000th the diameter of a proton. The entire length of the detector shifted by less than the width of a single atomic nucleus. That these distortions can be measured at all is one of the most extraordinary achievements in the history of science. But we are getting ahead of ourselves. Before we reach the detectors, we need to understand what kinds of events produce gravitational waves powerful enough to be noticed across billions of light years of space. That is where we are headed next.
What?
Chapter 3. The Prediction, Einstein's Gravitational Waves. In November of 1915, Albert Einstein completed the general theory of relativity. It was the culmination of nearly a decade of work, a period he later described as the most intense and exhausting intellectual effort of his life. The theory replaced Newton's picture of gravity with a geometric description of space-time, and it made predictions that nobody had yet tested and that many physicists found difficult to accept. One of those predictions came the following year. In 1916, Einstein published a paper in which he showed that his field equations, the mathematical heart of general relativity, allowed for wave-like solutions. When a massive object accelerates, it disturbs the curvature of space-time around it, and that disturbance propagates outward at the speed of light. He called them gravitational waves. The mathematics was clear. The physical interpretation was less so, even to Einstein himself. Over the following years, Einstein returned to the question several times, and his confidence in the reality of gravitational waves fluctuated. In 1936, working with his colleague Nathan Rosen, he submitted a paper to a journal claiming that gravitational waves did not actually exist, that they were a mathematical artifact of the coordinate system being used rather than a genuine physical phenomenon. The paper was sent out for review, and the reviewer identified significant errors in the argument. Einstein, initially irritated by the rejection, eventually came to agree that the reviewer was correct. The revised paper, published later that year, reversed its conclusion. Gravitational waves were real. This episode is sometimes cited as one of the earliest examples of peer review, catching a significant error, even in a paper by one of the greatest physicists who ever lived. But even after accepting their mathematical reality, Einstein believed gravitational waves would never be detected, and his reasoning was straightforward. The effect of a gravitational wave on matter is extraordinarily small. The waves lose almost no energy as they travel, which is part of what makes them scientifically valuable. But it also means they interact with matter so weakly that detecting them seemed, in the 1910s and for decades afterward, essentially impossible. Einstein was not alone in this view. For much of the 20th century, gravitational waves occupied an uncertain place in physics. Some researchers questioned whether they carried energy at all. The debate was not fully resolved until the 1950s and 1960s, when a series of thought experiments and theoretical arguments established conclusively that gravitational waves do carry energy and do have measurable physical effects. The clearest early evidence came not from a detector, but from a pair of stars. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a remarkable object using the Arecibo radio telescope in Puerto Rico. They found a pulsar, a rapidly rotating neutron star that emits regular pulses of radio waves, in orbit with another neutron star. The system was named PSRB 1913+16, and it quickly became one of the most valuable laboratories in astrophysics. Because pulsars pulse with extraordinary regularity, they function as precise natural clocks. By monitoring the timing of the pulses over years and then decades, Hulse and Taylor were able to measure the orbital period of the two neutron stars with great precision. And what they found was exactly what general relativity predicted. The orbit was shrinking. The two stars were spiraling slowly toward each other, losing energy at a rate that matched Einstein's equations for gravitational wave emission to within a fraction of a percent. This was not a direct detection. Nobody had measured the waves themselves, but it was compelling indirect evidence that gravitational waves exist, that they carry energy away from accelerating masses, and that general relativity's predictions about them are correct. Hulse and Taylor received the Nobel Prize in Physics in 1993 for the discovery. The question that remained was whether anyone could build an instrument capable of detecting gravitational waves directly, whether the distortion of space-time as a wave passed through could be measured against all the noise of a vibrating, trembling, electrically buzzing world. That question would take another 4 decades to answer. Chapter 4. What creates gravitational waves? Not everything that moves creates gravitational waves worth mentioning. A person walking across a room disturbs space-time. A planet orbiting a star sends ripples outward. Even the Earth and Moon, circling their common center of mass, produce gravitational waves. But the waves generated by ordinary motion at ordinary scales are so vanishingly small that no instrument could ever detect them and no meaningful effect could ever be observed. For gravitational waves to be strong enough to matter, something extraordinary has to happen. The universe needs to bring together objects of immense mass, moving at tremendous speeds, changing direction, or accelerating violently. The events that produce detectable gravitational waves are among the most energetic phenomena the universe is capable of generating. The most powerful sources fall into a few broad categories. The first and most productive source, in terms of what we have actually detected, is the merger of two black holes. When two black holes orbit each other, they lose energy through gravitational wave emission and gradually spiral inward. As the orbit tightens, they move faster. As they move faster, they radiate more energy. As they radiate more energy, the orbit tightens further. The process accelerates, the waves grow stronger, until the two black holes collide and merge into a single, larger black hole. The final fraction of a second before merger releases an almost incomprehensible burst of gravitational wave energy, more power than the combined light output of every star in the observable universe, compressed into a moment. The gravitational waves produced during a black hole merger have a characteristic shape. They begin as a slow, quiet oscillation, barely distinguishable from background noise. Over time, they increase in both frequency and amplitude, building toward a peak at the moment of merger. Then they die away rapidly as the newly formed black hole settles into a stable shape, a process called ringdown, which produces its own distinctive signal. This pattern, a gradual rise followed by a sharp peak and a decay, is called a chirp because when converted to sound, it resembles the brief upward sweep of a bird call. The second major source is the merger of two neutron stars. Neutron stars are the remnants of massive stars that have ended their lives in supernova explosions. They are extraordinarily dense, packing roughly the mass of the Sun into a sphere only about 20 kilometers across. When two neutron stars orbit each other and spiral inward, they produce gravitational waves in much the same way black holes do. But neutron star mergers have an additional feature. Unlike black holes, neutron stars are made of matter. When they collide, the collision produces not only gravitational waves, but also an explosion of light across the entire electromagnetic spectrum, from gamma rays to visible light to radio waves. This combination of gravitational and electromagnetic signals from the same event was first observed in 2017, and it opened an entirely new chapter in astronomy. We will come back to that story in detail later. A third source is the collision between a neutron star and a black hole. These mixed mergers are expected to produce gravitational waves, and the first confirmed detections of this type were announced in 2021. Depending on the relative masses of the two objects, the neutron star may be torn apart by tidal forces before it reaches the black hole, or it may be swallowed whole. The difference affects the gravitational wave signal and the presence or absence of accompanying light. Beyond mergers, other sources of gravitational waves exist, though most have not yet been directly detected. Rapidly rotating neutron stars, including pulsars, may produce continuous gravitational waves if they are not perfectly spherical. Even a tiny asymmetry in a neutron star spinning hundreds of times per second would generate a steady, quiet hum of gravitational radiation. No such continuous signal has been confirmed yet, but searches are ongoing. supernovae, the explosive deaths of massive stars, are expected to produce gravitational waves if the collapse and explosion are asymmetric. A perfectly symmetric explosion would produce no net gravitational wave emission. But real supernovae are turbulent and irregular, and the convulsive motion of the collapsing core should generate a burst of waves. Detecting supernova gravitational waves would provide a direct view into the heart of the explosion, a region completely hidden from optical telescopes. Finally, there is the possibility of a gravitational wave background, a faint, diffuse hum of waves produced by the superposition of countless mergers and other events throughout the history of the universe, stretching back to the earliest moments after the Big Bang. This background has not yet been directly detected, though there is growing evidence from pulsar timing arrays that something consistent with it may already be within reach. Each of these sources tells a different story about the universe. Each produces waves with different frequencies, different amplitudes, different signatures. Learning to read those signatures is the work of an entirely new branch of astronomy, one that is still in its earliest years. But before we can read the signals, we need to understand how the waves themselves travel from their source across the universe to us. Chapter 5. How Gravitational Waves Travel. A gravitational wave leaves its source and moves outward through the universe at the speed of light. Not approximately the speed of light, exactly the speed of light. This was one of the predictions of general relativity, and it was confirmed directly in 2017 when gravitational waves and light from the same neutron star merger arrived at Earth within 2 seconds of each other, after traveling approximately 130 million light-years. 2 seconds across 130 million light-years is, for all practical purposes, simultaneous. The measurement placed extraordinarily tight constraints on any difference between the speed of gravitational waves and the speed of light, confirming that they are, to at least 15 decimal places, the same. This matters for several reasons. It rules out certain alternative theories of gravity that predicted gravitational waves might travel at a different speed. It also means that gravitational waves carry information about their source in real time, in the same sense that light does. When we detect a gravitational wave, we are receiving a signal that left its source at the same moment the light did, and both have been traveling toward us ever since. Unlike light, however, gravitational waves are not absorbed or scattered by matter. Light can be blocked by dust clouds, absorbed by gas, scattered by plasma. The early universe was so dense and hot that light could not travel freely through it for the first 380,000 years. Everything that happened before that moment is hidden from our optical telescopes behind an opaque wall of glowing plasma. Gravitational waves pass through all of it without interruption. They travel through stars, through galaxies, through the densest matter in the universe, without losing their shape or their information. In principle, gravitational waves from the first fractions of a second after the Big Bang could still be traveling through the universe today, carrying direct information about conditions that no other messenger could ever reveal. This penetrating quality is one of the things that makes gravitational wave astronomy so scientifically compelling. It is not just a new way of seeing the universe. It is a way of seeing parts of the universe that are permanently invisible to every other instrument we have ever built. As a gravitational wave travels, It stretches and compresses space in a very specific pattern. The wave is transverse, meaning it affects directions perpendicular to the direction it is traveling, not the direction of travel itself. If a gravitational wave is moving toward you, it will alternately stretch space horizontally while compressing it vertically, then compress it horizontally while stretching it vertically. This alternating pattern repeats at the frequency of the wave. The two perpendicular directions affected by the wave are called its polarizations, and gravitational waves from general relativity have two polarization states referred to as plus and cross, after the shapes they trace out in space. The plus polarization stretches space along one axis and compresses it along the perpendicular axis, like the arms of a plus sign alternately lengthening and shortening. The cross polarization does the same thing but rotated 45 degrees, so the affected axes are diagonal. Real gravitational wave signals typically contain a mixture of both polarizations, and the relative amounts depend on the orientation of the source relative to the detector. This polarization structure is a direct prediction of general relativity. Alternative theories of gravity sometimes predict additional polarization states. Measuring the polarization of gravitational waves is therefore a way of testing whether general relativity is the correct description of gravity, or whether some other theory fits the data better. With multiple detectors operating simultaneously in different locations and orientations, it becomes possible to decompose the incoming signal into its polarization components and compare them against theoretical predictions. The amplitude of a gravitational wave, the degree to which it stretches and compresses space, is described by a quantity called the strain, usually written as h. The strain is defined as the fractional change in distance caused by the wave. A strain of 1 part in 1,000 means that a detector 1 meter long would change in length by 1 millimeter. A strain of 1 part in 10 to the 21, which is roughly the strain produced by the first detected gravitational wave at Earth, means that a detector 1 meter long would change in length by 1/10,000th the diameter of a proton. It is worth pausing on that number. 10 to the 21 is a 1 followed by 21 zeros. The fractional change in length is so small that it is difficult to find a meaningful comparison. If you stretch the distance from Earth to the nearest star, Proxima Centauri, about 4 light-years away by the same fractional amount, the change in distance would be roughly the width of a human hair. That is what the detectors are measuring. That is the signal buried in the noise of a vibrating planet, extracted using lasers and mirrors and decades of engineering refinement. The strain of a gravitational wave decreases as it travels. Specifically, it decreases in proportion to the distance from the source. Double the distance and the strain is halved. This is different from the way energy behaves with distance. Energy falls off as the square of the distance. Strain falls off linearly. This means that gravitational wave detectors are, in a sense, more efficient at reaching distant sources than detectors that measure energy directly. Every time you double the sensitivity of a gravitational wave detector, you do not double the volume of the universe you can observe. You increase it by a factor of 8, because you are reaching twice as far in every direction. This scaling has important practical consequences. Modest improvements in detector sensitivity translate into large increases in the detectable volume of the universe, and therefore large increases in the rate at which mergers and other events can be detected. The upgrades planned for existing detectors and the new facilities under development will not just see farther. They will see into a volume of space that dwarfs what current instruments can access. The frequency of a gravitational wave is determined by the dynamics of its source. Merging black holes produce waves in the frequency range that LIGO is designed to detect, roughly between 10 and a few thousand cycles per second, which happens to overlap with the range of human hearing. This is why the famous audio representations of gravitational wave detections are not merely illustrative. They are, in a real sense, accurate translations of the wave's oscillation into sound. The chirp of GW 150914, the first detected gravitational wave event, lasts about a fifth of a second and sweeps upward in frequency from about 35 Hz to about 150 Hz before the merger. Played through a speaker, it sounds like a brief, soft thump, unremarkable to the ear, extraordinary in its meaning. Different sources produce waves at very different frequencies. Supermassive black hole mergers, involving objects millions or billions of times the mass of the Sun, produce waves at extremely low frequencies, far below anything LIGO can detect. These are the targets of future space-based detectors and of pulsar timing arrays, which use the regular ticking of distant pulsars as a kind of cosmic ruler to detect the slow, long wavelength undulations of very low-frequency gravitational waves passing through the galaxy. At the other end of the spectrum, certain dense neutron star phenomena may produce gravitational waves at frequencies of kilohertz or higher, at the upper edge of or beyond LIGO's current sensitivity range. Expanding detector capabilities across a wider range of frequencies is one of the central goals of gravitational wave astronomy over the coming decades. Between the source and the detector, gravitational waves travel unimpeded. They carry their information faithfully across whatever distance separates origin from observer. They do not age. They do not degrade. They arrive after millions or billions of years of travel as a precise record of the event that created them, encoded in the stretching and compressing of space itself. What they need, when they finally arrive, is something sensitive enough to notice them. Chapter 6. Detecting the Undetectable, LIGO. The idea of building a machine to detect gravitational waves is, on its face, almost absurd. The signals are unimaginably small. The sources are billions of light years away. The effect on any detector on Earth is a fractional change in length, so minute that it makes the width of a single proton seem comparatively large. And the detector has to operate on the surface of a planet that is constantly vibrating, shaking with the footsteps of people, the movement of traffic, the churning of the ocean, the distant rumble of earthquakes, and the thermal motion of its own atoms. To detect a gravitational wave, you have to measure a change in distance smaller than anything that has ever been measured in the history of science against a background of noise that is, by comparison, deafening. And yet it was done. The story of how it was done begins in the early 1970s when a physicist named Rainer Weiss at the Massachusetts Institute of Technology began thinking seriously about what kind of instrument might be capable of detecting gravitational waves. Weiss had been teaching a course on general relativity and had set himself the problem of working out the practical requirements for a detector. What he arrived at was the basic concept of a laser interferometer, a device that uses light to measure distances with extraordinary precision. The principle is elegant. A laser beam is split into two beams that travel down two long perpendicular arms. At the end of each arm, a mirror reflects the beam back toward the starting point. The two returning beams are recombined, and because light behaves as a wave, the combined beam shows an interference pattern that depends on the difference in the lengths of the two arms. If the arms are exactly the same length, the beams cancel each other out perfectly when recombined, and no light reaches the detector. If one arm is even slightly longer or shorter than the other, the cancellation is imperfect, and some light gets through. The amount of light that reaches the detector is a precise measure of the difference in arm lengths. When a gravitational wave passes through the detector, it stretches one arm while compressing the other, then reverses. This alternating change in the relative lengths of the arms disturbs the interference pattern in a characteristic way. By monitoring the output of the detector with sufficient precision, it should be possible to detect the passage of the wave. The challenge is that the changes in arm length caused by gravitational waves are unimaginably small. To detect the waves produced by distant black hole mergers, the detector needs to be sensitive to changes in length of about 1,000th the diameter of a proton across arms several kilometers long. This requires controlling every possible source of noise with extraordinary care. Weiss worked out the noise budget in detail, identifying the main sources of interference and estimating what it would take to bring each one under control. Seismic noise, the vibration of the ground, had to be isolated. Thermal noise, the random motion of atoms in the mirrors and their suspensions, had to be minimized. Shot noise, the quantum uncertainty in the arrival of individual photons at the detector, had to be reduced by using very high laser power. Each of these challenges required its own solution, and each solution created new engineering problems that in turn required further solutions. Around the same time, the physicist Kip Thorne at the California Institute of Technology was developing theoretical models of gravitational wave sources, working out what kinds of signals detectors might expect to see from merging black holes and neutron stars. Thorne became a powerful advocate for building a large-scale interferometer, and he and Weiss eventually joined forces with Ronald Drever, an experimentalist from Scotland who had been building prototype interferometers at Caltech. Together, the three of them formed the scientific core of what would become the LIGO project. LIGO stands for Laser Interferometer Gravitational Wave Observatory. The project received funding from the National Science Foundation in the 1990s, and construction began on two facilities, one in Hanford, Washington, in the Pacific Northwest, and one in Livingston, Louisiana, in the American South. The two facilities are separated by about 3,000 kilometers, a separation that is crucial for distinguishing genuine gravitational wave signals from local noise. A truck driving past one detector might cause a vibration that looks superficially like a signal, but the same truck cannot simultaneously cause the same vibration at a detector 3,000 kilometers away. A real gravitational wave, traveling at the speed of light, would arrive at both detectors within about 10 milliseconds of each other, with a time delay that depends on the direction the wave is coming from. Each LIGO detector has two arms, each 4 kilometers long. The arms are housed in steel vacuum tubes because even air molecules would scatter the laser light and introduce noise. The vacuum inside the tubes is one of the best vacuums ever created on Earth, far emptier than the space between planets in the solar system. The mirrors at the ends of the arms, called test masses, are made of the purest fused silica glass, polished to a smoothness measured in atoms. Each mirror weighs about 40 kilograms and hangs from a sophisticated 4-stage pendulum suspension system designed to isolate it from ground vibrations across a wide range of frequencies. The laser itself does not simply travel down the arm once and return. The arms are configured as optical cavities with mirrors at each end that bounce the light back and forth hundreds of times before it is recombined. This effectively multiplies the length of the arms by the number of bounces, increasing the detector's sensitivity without requiring physically longer arms. The light inside the arms carries about 100 kilowatts of power, enough to cause serious damage if it were to escape the optical system. Even with all of these precautions, the detector is sensitive to an enormous range of disturbances. Wind loading on the buildings causes vibrations. Temperature changes cause the equipment to expand and contract. Distant earthquakes register clearly. Passing trains have been detected. The ocean, hundreds of kilometers away, generates a constant low-frequency rumble from waves crashing on the shore, a noise source called microseismic noise that sets a floor on what LIGO can detect at very low frequencies. Managing all of this noise requires constant monitoring and active feedback systems that measure vibrations and apply corrective forces to cancel them out. The seismic isolation systems alone involve multiple stages of passive and active damping, each stage reducing the transmitted vibration by orders of magnitude. The final stage, the mirror itself, hangs at the end of this chain, isolated from the world as completely as human engineering can manage. The original LIGO detectors, which began operating in 2002, were not sensitive enough to detect gravitational waves. They ran for several years without a confirmed detection, which was expected. The goal of the initial detectors was to demonstrate that the technology worked, to identify and understand all the noise sources, and to develop the techniques needed for the next generation of instruments. Between 2010 and 2015, the detectors were shut down for a comprehensive upgrade program. Nearly every component was improved or replaced. The laser power was increased. The mirror suspensions were redesigned. The seismic isolation systems were upgraded. Quantum optical techniques were introduced to reduce shot noise. When the upgraded detectors, now called Advanced LIGO, came back online in September 2015, their sensitivity had improved by roughly a factor of 10 compared to the original instruments. That factor of 10 in strain sensitivity corresponded to a factor of 1,000 in the volume of the universe the detectors could survey. They had been running in their new configuration for less than 2 days when the signal arrived. It came on September 14, 2015, at 5:51 in the morning, Eastern Daylight Time. The Livingston detector registered it first, followed 6.9 milliseconds later by the Hanford detector. The signal lasted about 0.2 of a second. It swept upward in frequency from about 35 Hz to about 150 Hz, then cut off abruptly. The strain at its peak was about 1 part in 10 to the 21. the automated detection systems flagged it within minutes. Physicists reviewing the data recognized it almost immediately for what it was. The signal matched, with extraordinary precision, the theoretical predictions for the merger of two black holes, one about 36 times the mass of the Sun and one about 29 times the mass of the Sun, located about 1.3 billion light-years away. For months, the LIGO team analyzed the data exhaustively, searching for any possible alternative explanation. They tested whether the signal could have been injected artificially as a blind test of the analysis pipeline. It had not been. They searched for any instrumental artifact that could have produced a false signal with the same characteristics. They found none. They ran the data through every statistical test they could devise. On February 11, 2016, they announced the result to the world. Gravitational waves had been detected. Einstein's prediction, made a century earlier, had been confirmed, and a new era in astronomy had begun. Chapter 7. The first detection, GW 150914. On the morning of September 14, 2015, most of the scientists working on the LIGO project were asleep. The detectors had only recently been brought back online after the years-long upgrade program, and the collaboration was still in the process of commissioning the instruments, fine-tuning their performance, and preparing for the formal start of the observing run, which was scheduled to begin 3 days later. The detection that changed astronomy forever arrived. In other words, before the experiment had officially started. The signal reached the Livingston detector in Louisiana first, at 5:51 and 26 seconds in the morning, Eastern Daylight Time. 6.9 milliseconds later, it arrived at the Hanford detector in Washington. The time delay between the two sites was consistent with a gravitational wave traveling at the speed of light from a direction in the southern sky. The automated analysis pipelines that monitored the detector output flagged the event within minutes. A physicist named Marco Drago, working at the Albert Einstein Institute in Hanover, Germany, was among the first to see the alert. He looked at the data and immediately recognized the characteristic shape of a binary merger signal. He sent a message to colleagues noting that the event looked like it could be real. In the hours and days that followed, as more people examined the data, that initial impression hardened into conviction. But the LIGO collaboration is nothing if not careful. The history of gravitational wave detection is littered with false alarms, instrumental artifacts, and signals that turned out to have mundane explanations. The collaboration had developed rigorous protocols for evaluating candidate events, and they applied every one of them to this signal. One of the first things they checked was whether the signal was a blind injection, a fake signal deliberately inserted into the data stream by a small group of people within the collaboration as a test of the analysis pipeline. The practice of blind injections had been used in previous LIGO science runs to ensure that the analysis teams could correctly identify and characterize a signal without knowing in advance whether it was real. The team responsible for injections was contacted and confirmed that no injection had been made. The signal was not a test. They then searched for any environmental disturbance that could have produced a correlated signal at both detectors simultaneously. Seismic sensors, magnetometers, microphones, radio frequency monitors, and dozens of other instruments continuously record the environment around each detector. Every recorded disturbance in the minutes surrounding the event was examined. Nothing was found that could account for a signal of the observed characteristics appearing at both sites within 6.9 milliseconds. The signal itself was analyzed in extraordinary detail. Its duration, frequency evolution, amplitude, and phase were all compared against a library of theoretical waveforms computed from general relativity for merging black holes of various masses and spins. The best match was a system consisting of two black holes, one with a mass of about 36 times that of the Sun, and one with a mass of about 29 times that of the Sun, merging at a distance of approximately 1.3 billion light-years. The merger produced a final black hole with a mass of about 62 times that of the Sun. The difference between the combined mass of the two original black holes, 65 solar masses, and the mass of the final black hole, 62 solar masses, represents the energy radiated as gravitational waves during the merger. 3 solar masses of energy converted directly into gravitational radiation in a fraction of a second. 3 solar masses. Each solar mass is roughly 2 times 10 to the power of 30 kilograms. Using Einstein's equation relating energy and mass, 3 solar masses corresponds to an energy of about 5 times 10 to the power of 47 joules. The total energy output of the Sun over its entire 10 billion year lifetime is approximately 1.2 times 10 to the power of 44 joules. The gravitational wave emission from GW 150914 released, in less than a second, roughly 1,000 times more energy than the Sun will produce over its entire life. Nearly all of that energy passed through the Earth without depositing so much as a fraction of a joule in any detector. The interaction of gravitational waves with matter is so weak that even this colossal energy release left a trace measurable only in the most sensitive instrument ever constructed. The statistical significance of the detection was calculated to be greater than 5 sigma, the standard threshold in physics for claiming a discovery. This means that the probability of the signal arising from random noise fluctuations was less than 1 in 3.5 million. In the months of analysis that followed the detection, no alternative explanation was found. Every test the collaboration applied was consistent with the signal being a real gravitational wave from a binary black hole merger, exactly as described by general relativity. The formal announcement was made on February 11, 2016, at a press conference held simultaneously in Washington, D.C., Hanover, and other locations around the world. The principal spokespersons for the LIGO and Virgo collaborations presented the result. Rainer Weiss, Kip Thorne, and Barry Barish, who had led the LIGO project through its construction and commissioning phases, were present. The room was filled with journalists, physicists, and dignitaries. Outside, millions of people watched a live stream. Weiss spoke first. He described the signal and its analysis in careful, measured terms. Thorne spoke about its theoretical significance. When the audio representation of the signal was played, the brief chirp lasting less than a second, the room was quiet for a moment before breaking into applause. The response from the scientific community and the public was extraordinary. Within hours, the announcement had been covered by every major news organization in the world. The paper describing the detection, published simultaneously in physical review letters became one of the most widely read scientific papers in history. It had over 1,000 authors, reflecting the scale of the collaboration that had made the detection possible. For the physicists who had spent their careers building LIGO, many of whom had devoted decades to the project with no guarantee that a detection would ever come, the announcement was deeply personal. Some had begun their careers in gravitational wave physics as graduate students in the 1970s and 1980s, at a time when the field was considered by many mainstream physicists to be a long shot at best. They had endured years of incremental progress, repeated setbacks, and the skepticism of colleagues who doubted the project would ever succeed. Rainer Weiss, Kip Thorne, and Barry Barish were awarded the Nobel Prize in Physics in 2017 for their decisive contributions to the LIGO detector and the observation of gravitational waves. Ronald Drever, who had been a co-founder of the project alongside Weiss and Thorne, died in March 2017, several months before the Nobel announcement. The prize is not awarded posthumously, and his absence from the recognition was noted with sadness by many in the field. But the detection of GW 150914 was more than a confirmation of a century-old prediction. It was a discovery in its own right. Before September 14, 2015, the existence of binary black hole systems, two black holes orbiting each other and eventually merging, had never been directly confirmed. Black holes themselves had been inferred from their effects on surrounding matter and light, but never observed interacting directly with each other. GW 150914 provided the first direct evidence that binary black hole systems exist, that they merge on timescales accessible to human observation, and that the mergers produce gravitational waves exactly as general relativity predicts. It also told us something about the black holes themselves. The masses of the two objects, 36 and 29 solar masses, were larger than most astronomers had expected for stellar mass black holes. Black holes formed from the collapse of individual stars were generally thought to have masses below about 25 solar masses, based on models of stellar evolution and the mass loss that occurs during a star's lifetime. The discovery of black holes significantly more massive than this raised new questions about how they formed and what kinds of stellar environments could produce them. In the years following the first detection, LIGO and its partner detector Virgo, located near Pisa in Italy, have detected dozens of additional gravitational wave events. Each one has added to the catalogue of binary mergers and provided new data on the population of black and holes and neutron stars in the universe. The signals have ranged from black hole mergers involving objects of just a few solar masses to mergers involving black holes of more than 100 solar masses. Each detection has been a new data point in an emerging picture of how compact objects form, evolve, and eventually collide across cosmic time. The first detection was, in retrospect, almost perfectly timed. The detectors had been upgraded to their new sensitivity just days before the signal arrived. Had the upgrade taken longer, had any number of technical problems delayed the commissioning process, GW 150914 might have passed through the Earth undetected, as it had passed through everything else in its 1.3 billion year journey across the universe. Instead, for the first time in the history of our species, we heard the universe speak in a language older than light. Chapter 8. What gravitational waves reveal. The detection of gravitational waves was not simply the confirmation of a prediction, it was the opening of a new sense. For all of human history, our understanding of the universe had been built almost entirely on light. Visible light first, then radio waves, then infrared and ultraviolet, then X-rays and gamma rays. Each new part of the electromagnetic spectrum that we learned to detect revealed aspects of the universe that had been invisible before. Radio astronomy showed us pulsars and quasars. X-ray astronomy revealed neutron stars and the hot gas surrounding black holes. Infrared astronomy allowed us to peer through dust clouds into the hearts of forming galaxies. Each extension of our electromagnetic vision was transformative, but all of these are variations on the same fundamental messenger. They are all forms of electromagnetic radiation, all photons, all subject to the same limitations. They can be absorbed, they can be scattered, they can be blocked, and they can only tell us about matter and energy that emits, reflects, or absorbs light in some form. Gravitational waves are something categorically different. They are not electromagnetic. They are not blocked by matter. They do not require a luminous source. They carry information about the dynamics of mass itself, about the motion and acceleration of objects regardless of whether those objects emit any light at all. Two black holes merging a billion light-years away produce no light whatsoever. Before gravitational wave astronomy, that merger was completely invisible to us. Now it is one of the clearest signals we can detect. This is what astronomers mean when they describe gravitational wave astronomy as opening a new window on the universe. It is not a metaphor for incremental improvement. It is a genuinely new kind of information, arriving through a channel that has never been accessible before. The most dramatic illustration of what gravitational waves can reveal came on August 17, 2017, with an event designated GW 170817. On that morning, the LIGO and Virgo detectors registered a gravitational wave signal unlike any previously detected. Where the black hole mergers had produced signals lasting a fraction of a second, this signal lasted nearly 2 minutes. It chirped upward in frequency over that entire duration, growing slowly louder and higher pitched as the source spiraled inward. The character of the signal identified it immediately as a neutron star merger. Two neutron stars orbiting each other and spiraling together under the influence of their mutual gravity and the energy they were losing to gravitational wave emission. 98 seconds after the gravitational wave signal ended, a gamma ray burst was detected by the Fermi Gamma Ray Space Telescope and the Integral satellite. The burst was short, lasting only about 2 seconds, and it came from the same region of the sky as the gravitational wave source. This was the first time a gravitational wave event had been accompanied by an electromagnetic signal, and it confirmed something theorists had long predicted. The merger of two neutron stars produces not only gravitational waves, but also a powerful burst of gamma radiation, the most energetic form of light in the universe. Within hours, dozens of telescopes around the world and in space were pointed at the source. What they found was a kilonova, an explosion produced by the collision of the two neutron stars, glowing across a wide range of wavelengths. Over the following days and weeks, the kilonova faded and evolved. its color shifting from blue to red as the ejecta expanded and cooled. The observations told a remarkable story. Neutron stars are made of matter compressed to densities far beyond anything achievable in a laboratory. The outer layers of a neutron star contain heavy atomic nuclei arranged in a crystalline lattice. The inner layers are thought to contain matter in more exotic states, possibly including free quarks or other forms of dense nuclear material that do not exist anywhere else in the observable universe. When two neutron stars collide, some of this material is ejected at a significant fraction of the speed of light, and in the extreme conditions of the merger, nuclear reactions occur that produce heavy elements. The spectroscopic analysis of GW 170817's kilonova showed clear signatures of heavy elements being synthesized in real time. Among the elements detected were strontium and, most significantly, large quantities of gold and platinum. The observations confirmed what theorists had suspected for decades. A significant fraction of the heavy elements in the universe, including all the gold that has ever existed, was forged in the violent collisions of neutron stars. Every gold ring, every gold coin, every piece of gold jewelry that has ever existed on Earth contains atoms that were created in the merger of neutron stars somewhere in the galaxy, billions of years before the solar system formed. Those atoms were scattered through space by the explosion, incorporated into the interstellar medium, and eventually gathered up by the cloud of gas and dust that collapsed to form the Sun and its planets. The gold in your possession is older than the Earth. It is older than the solar system. It was born in fire and gravity, in a collision so violent that it shook the fabric of space itself. GW 170817 was observed by over 70 telescopes and observatories across the world and in space, spanning the full range of the electromagnetic spectrum from radio to gamma rays. It was the most extensively observed astronomical event in history. The scientific output was enormous. Within months, more than 100 scientific papers had been published analyzing different aspects of the observations. Among the results was a new measurement of the Hubble constant, the parameter that describes the rate at which the universe is expanding. The Hubble constant can be measured in two ways that have historically given somewhat different answers. One method uses the cosmic microwave background, the afterglow of the Big Bang, to infer the expansion rate of the early universe and extrapolate forward. Another uses the observed brightnesses and recession velocities of distant galaxies. For years, the two methods have given results that disagree slightly, a discrepancy known as the Hubble tension that has been a source of significant concern among cosmologists. Gravitational waves offer a third, independent method. Because the shape of a gravitational wave signal from a binary merger encodes information about the masses of the objects and the distance to the source, it is possible to determine the distance to the merger directly from the gravitational wave data alone, without any assumptions about the cosmic distance ladder. By combining this distance with the recession velocity of the host galaxy, measured from the redshift of its light, it is possible to estimate the Hubble constant independently of either of the two traditional methods. The measurement from GW 170817 gave a value that fell between the two existing estimates, though with an uncertainty large enough to be consistent with either. As more neutron star mergers are detected and the statistics improve, this gravitational wave method of measuring the Hubble constant will become increasingly precise and may eventually help resolve the tension between the two traditional approaches. Beyond GW170817, the growing catalogue of gravitational wave detections has begun to reveal the population of compact objects in the universe in a way that was previously impossible. Before gravitational wave astronomy, the known population of stellar mass black holes numbered in the dozens, all inferred from X-ray observations of black holes actively accreting matter from companion stars. The gravitational wave catalogue has added dozens more, and the sample is now large enough to begin drawing statistical conclusions about the distribution of black hole masses, spins, and merger rates. Some of the detections have been surprising. Several mergers have involved black holes with masses in the range of 50 to 100 solar masses, a region that stellar evolution theory suggested should be largely empty. Stars massive enough to form black holes in this mass range are expected to undergo a process called pair instability, in which the core of the star becomes unstable and the star is completely disrupted before it can collapse to a black hole. The observation of black holes in this mass gap raises questions about alternative formation pathways, possibly involving the merger of smaller black holes in dense stellar environments such as globular clusters or the disks of active galactic nuclei. Other detections have revealed neutron star and black hole masses that challenge existing models of how these objects form. One event, designated GW190814, involved the merger of a black hole about 23 times the mass of the Sun with a compact object about 2.6 times the mass of the Sun. The lighter object falls in a range where it is unclear whether it is a very massive neutron star or a very light black hole. The maximum mass of a neutron star is set by the equation of state of dense nuclear matter, a quantity that is not precisely known. If the 2.6 solar mass object is a neutron star, it is the most massive neutron star ever observed and places strong constraints on what neutron star interiors are made of. If it is a black hole, it is the lightest black hole ever observed, and its existence requires explanation. Each of these puzzles is, in a sense, a gift. They are places where our current understanding is incomplete, where the data is telling us that something is happening in the universe that our theories do not fully account for. The history of astronomy is a history of such gifts, of observations that did not fit the existing picture and forced a revision of our understanding. Gravitational wave astronomy is generating these gifts at a remarkable rate, and the observing runs are still in their early stages. There is also the matter of testing general relativity itself. Every gravitational wave detection is an opportunity to check whether the signal behaves as general relativity predicts. The theory makes specific predictions about the relationship between the masses and spins of the merging objects and the shape of the resulting waveform. It predicts the rate at which the orbit decays due to gravitational wave emission. It predicts the properties of the ring-down signal as the final black hole settles into its equilibrium state. In every case tested so far, the observations have been consistent with general relativity to high precision. This is not a trivial result. General relativity has been tested extensively in the weak field regime, in situations where gravity is relatively gentle, such as the solar system and binary pulsars. Gravitational wave observations probe the strong field regime, where space-time curvature is extreme and the velocities involved are a significant fraction of the speed of light. These are conditions where deviations from general relativity, if they exist, would be most likely to manifest. So far, no deviations have been found. General relativity continues to pass every test we can devise, but the tests will become more stringent as the detectors improve and the catalogue grows. If general relativity is an approximation to some deeper theory of gravity, as many physicists suspect it must be, gravitational wave observations may eventually reveal the cracks. The universe has been sending us these signals since long before our planet existed. Black holes have been merging, neutron stars have been colliding, and the ripples from those events have been spreading outward through the cosmos for billions of years. Most of them have passed through the Earth unnoticed, stretching and compressing space by amounts too small to measure. Now, for the first time, we are listening. And what we are hearing is already rewriting our understanding of the most extreme objects and events in the universe. What remains to be heard may rewrite it further still. Chapter 9. The Future of Gravitational Wave Astronomy. We are, by any reasonable measure, at the very beginning of gravitational wave astronomy. The first detection occurred less than a decade ago. The catalogue of confirmed events, while growing rapidly, still numbers in the hundreds. The detectors currently in operation, remarkable as they are, represent only the first generation of instruments capable of making these observations. What comes next, in terms of both technology and scientific discovery, is likely to dwarf everything that has been achieved so far. To appreciate what the future holds, it helps to understand the current limitations of ground-based detectors like LIGO and Virgo. These instruments are extraordinarily sensitive, but they operate within a specific frequency band, roughly between 10 and several thousand hertz. This band is well matched to the gravitational waves produced by stellar mass compact object mergers, black holes and neutron stars with masses ranging from a few to a few hundred times that of the Sun. But the gravitational wave universe is far broader than this. There are sources producing waves at frequencies far below what any ground-based detector can access, and sources producing waves at frequencies far above. Each frequency band contains different populations of sources, different physical processes, different scientific questions. Accessing those bands requires fundamentally different kinds of instruments. At low frequencies, below about 1 Hertz, ground-based detectors are hopelessly compromised by seismic noise. No amount of isolation engineering can fully decouple a detector resting on the surface of the Earth from the constant vibration of the planet itself. To reach low frequencies, the detector has to leave the ground entirely. This is the motivation for LISA, the Laser Interferometer Space Antenna, a gravitational wave observatory that will operate in space. LISA is a mission of the European Space Agency with contributions from NASA and other partners, and it is currently scheduled for launch in the mid-2030s. The concept involves 3 spacecraft flying in a triangular formation, separated from each other by approximately 2.5 million kilometers, linked by laser beams that measure the distances between them with extraordinary precision. The arm length of 2.5 million kilometers compared to LIGO's 4 kilometers immediately suggests why a space-based detector can access much lower frequencies. The longer the arms, the lower the frequency of gravitational waves that can be detected. LISA is designed to operate in the frequency range of roughly 1/10,000th of a hertz to 1/10th of a hertz. In this band, the dominant sources are supermassive black hole mergers, the collisions of the black holes that sit at the centers of galaxies and have masses ranging from millions to billions of times that of the Sun. When galaxies merge, their central black holes eventually find each other, form as a binary system, and spiral together. The gravitational waves produced by these mergers are among the most powerful events in the universe, and LISA will be able to detect them across virtually the entire observable universe. LISA will also detect a class of sources called extreme mass ratio inspirals, or EMRs. These occur when a compact object of stellar mass, a black hole, neutron star, or white dwarf, falls into orbit around a supermassive black hole and slowly spirals inward over thousands of orbits before finally merging. The gravitational wave signal from an EMRI is extraordinarily complex, encoding detailed information about the geometry of spacetime in the immediate vicinity of the supermassive black hole. Analyzing EMRI signals will provide the most precise test of general relativity in the strong field regime ever performed, and may reveal whether the black holes at the centers of galaxies are exactly as general relativity describes them, or whether something more exotic is involved. Beyond LISA, there are proposals for even more ambitious space-based detectors. The Big Bang Observer and the Deci Hertz Interferometer Gravitational Wave Observatory, known as DXIGO, are concepts for the detectors that would bridge the gap between LISA's frequency band and LIGO's, accessing a range that contains sources currently out of reach of either instrument. These missions remain in the conceptual and early development stage, but they illustrate the breadth of the scientific program that gravitational wave astronomers envision over the coming century. On the ground, the next generation of detectors is already in the planning and early construction phase. Two major projects are underway. In Europe, the Einstein telescope is a proposed underground detector with arms 10 kilometers long, arranged in a triangular configuration rather than the L shape of LIGO and Virgo. Operating underground dramatically reduces seismic noise, and the triangular geometry allows the detector to measure both gravitational wave polarizations simultaneously, providing more complete information about each detected event. The Einstein telescope is designed to be sensitive to gravitational waves at frequencies as low as a few hertz, extending the observable range downward compared to current detectors, and its sensitivity at higher frequencies will be roughly 10 times better than advanced LIGO at its most sensitive. In the United States, the Cosmic Explorer project envisions detectors with arms 40 kilometers long, 10 times the length of LIGO's arms. The increase in arm length directly translates into improved sensitivity, and Cosmic Explorer is expected to be able to detect binary neutron star mergers anywhere in the observable universe. Where LIGO can currently detect neutron star mergers out to a few 100 million light-years, Cosmic Explorer would extend this reach to distances of 10 billion light-years or more, encompassing a volume of space billions of times larger than LIGO's current horizon. The scientific implications of this extended reach are profound. With the ability to detect mergers across cosmic time, gravitational wave astronomers will be able to trace the history of compact object formation from the present day back to the epoch when the first stars formed, just a few 100 million years after the Big Bang. The masses and merger rates of black holes and neutron stars at different cosmic epochs carry information about how stars formed and evolved under conditions very different from those in the universe today. The first stars, known as population 3 stars, formed from gas that contained only hydrogen and helium, with none of the heavier elements that make up most of the matter we are familiar with. They are thought to have been much more massive than typical stars today, and the black holes they left behind may have been correspondingly more massive. Cosmic Explorer may be able to detect the gravitational wave, signatures of mergers involving these primordial black holes, providing a direct observational window onto the universe's first stellar generation. At even lower frequencies, pulsar timing arrays are already beginning to probe a gravitational wave signal that no interferometric detector can access. Pulsars are rotating neutron stars that emit beams of radio waves with extraordinary regularity. The most stable pulsars keep time better than atomic clocks, their pulses arriving with a precision that varies by only a few hundred nanoseconds over years of observation. By monitoring an array of such pulsars distributed across the galaxy, astronomers can use the entire galaxy as a gravitational wave detector. A very low-frequency gravitational wave passing through the galaxy would cause slight variations in the arrival times of pulses from different pulsars in a correlated pattern that can be extracted from the data. In 2023, several pulsar timing array collaborations around the world, including the North American Nanohertz Observatory for gravitational waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, announced evidence for a gravitational wave background signal. The signal was consistent with a stochastic background of gravitational waves, a diffuse hum produced by the superposition of waves from countless supermassive black hole binaries throughout the universe. The evidence was compelling but not yet definitive, and the collaborations characterized it as strong evidence rather than a confirmed detection. If confirmed, this background signal will open an entirely new domain of gravitational wave science. The gravitational wave background carries information about the population of supermassive black holes across cosmic time, about the dynamics of galaxy mergers, and potentially about exotic processes in the early universe. Some models of the early universe predict that phase transitions, in which the universe underwent sudden changes in its physical state as it cooled after the Big Bang, would have produced a gravitational wave background with a characteristic spectrum. Detecting and characterizing this primordial background would provide direct observational evidence for processes that occurred in the first fractions of a second after the Big Bang, at energies far beyond anything achievable in any particle accelerator. This is perhaps the most extraordinary long-term prospect of gravitational wave astronomy. Light cannot reach us from before the moment of recombination, roughly 380,000 years after the Big Bang, because the universe before that time was an opaque plasma through which photons could not travel freely. The cosmic microwave background, the oldest light we can observe, is a snapshot of the universe at that moment, and it carries information about everything that happened before only indirectly through the imprints left on the plasma by earlier processes, Gravitational waves have no such limitation. They pass through plasma, through radiation, through matter of any density without interaction. Gravitational waves produced in the first fractions of a second after the Big Bang, by phase transitions, by the dynamics of cosmic inflation, by exotic processes involving hypothetical particles or fields, could still be propagating through the universe today. Detecting them would be the equivalent of receiving a message from the birth of the universe, carrying information about conditions and processes that are permanently hidden from every other kind of observation. The technical challenges involved in detecting a primordial gravitational wave background are immense. The signal is expected to be extraordinarily faint, buried beneath the foreground signals from compact object mergers and other astrophysical sources. Separating the primordial background from these foregrounds will require detectors of sensitivity far beyond what is currently achievable and analysis techniques that do not yet exist. But the scientific prize is so extraordinary that it has motivated serious long-term planning and research. There is also the matter of unexpected discoveries. Every time astronomy has opened a new observational window, the most significant discoveries have not been the ones that were predicted. Radio astronomy was developed with specific scientific goals in mind, but its most transformative discoveries, pulsars, quasars, the cosmic microwave background, were not anticipated. X-ray astronomy revealed an entire population of compact binary systems that had not been predicted. The pattern is consistent across the history of the field. New observational capabilities reveal a universe richer and stranger than theorists had imagined. Gravitational wave astronomy is almost certainly no different. The current catalogue of detections has already produced surprises: black holes in the mass gap, mergers between objects of very different masses, signals that push against the boundaries of existing theoretical models. As sensitivity improves and the catalogue grows from hundreds to thousands to tens of thousands of events, the surprises will accumulate. Some will be explicable within existing frameworks, filling in details of a picture that is already roughly correct. Others may require more fundamental revisions to our understanding. The universe has been vibrating with gravitational waves since its earliest moments. Every massive object that has ever accelerated, every star that has ever collapsed, every black hole that has ever merged, has sent ripples outward through the fabric of space-time. Most of those ripples have passed through the Earth unnoticed, stretching and compressing the planet and everything on it by amounts too small to perceive. We have been immersed in gravitational waves our entire lives without knowing it. Now we know, and we have built, after a century of theoretical development and decades of engineering effort, instruments capable of hearing them. The first signals we have detected are already extraordinary. They have confirmed Einstein's century-old prediction. They have revealed the existence of binary black hole systems. They have shown us the birthplace of gold. They have provided new ways to measure the expansion of the universe. They have tested general relativity in the most extreme conditions it has ever faced, and found it holding firm. And we are, by any measure, just at the beginning. The detectors will improve. New facilities will come online. New frequency bands will become accessible. The catalogue will grow. The surprises will accumulate. And with each new detection, with each new signal extracted from the noise, we will understand a little more about the universe we inhabit, about the objects within it, about the forces that shape it, and about the nature of space and time themselves. Somewhere in the universe, two black holes are spiraling toward each other right now. Their orbit is tightening. The gravitational waves they are producing are spreading outward at the speed of light in every direction. In some millions or billions of years, those waves may reach the Earth, or wherever our descendants happen to be, and if instruments exist to detect them, they will be heard. We have learned to listen. What we will hear next, we cannot fully predict, but the universe has no shortage of things to say. Chapter 10. A New Way of Listening. There is something quietly profound about the moment we find ourselves in. For the entirety of human history, our knowledge of the universe was built on light. Ancient astronomers mapped the stars with their eyes. Later generations built telescopes that gathered more light, reaching farther and seeing finer detail. Each advance in optics revealed more of the same kind of information, more photons from more distant sources, at more wavelengths. The universe we came to understand was, in a fundamental sense, a universe of light. That is no longer entirely true. On September 14th, 2015, for the first time in the history of our species, we detected something that was not light, not a particle, not a chemical signal, not a pressure wave traveling through a medium. We detected a ripple in the fabric of space-time itself, a distortion so small that it changed the length of a 4-kilometer tunnel by less than the width of a proton, produced by the merger of two black holes 1.3 billion light-years away, traveling across the universe for longer than the Earth has existed. We heard it. That word is not quite right, and yet it is the most honest one available. The signal, when converted to sound, lasts less than 1/5 of a second. It is barely audible, a soft upward sweep, unremarkable to anyone who does not know what they are listening to. But it is a sound produced not by air pressure or vibration, but by the universe itself changing shape, by space stretching and compressing as a wave passed through. It is worth sitting with that for a moment. We tend to think of the universe as something we observe from a distance. We point our telescopes outward and gather the light that arrives at our doorstep from distant sources. We are, in this picture, passive recipients of information that the universe happens to send in our direction. Gravitational waves change this picture in a subtle but important way. They do not travel through space. They are space moving. When a gravitational wave passes through the Earth, it does not merely brush against the planet from outside. It passes through everything, through the rock beneath our feet, through the air, through every atom in every living body. For the fraction of a second that the wave is present, the distances between every pair of points on Earth are slightly different from what they were a moment before. The wave does not visit us. It inhabits us briefly and then moves on. We are, in the most literal sense, part of the medium through which these waves travel. This is not a poetic embellishment. It is a physical fact that follows directly from general relativity, and it suggests something worth reflecting on as we consider what gravitational wave astronomy means beyond its immediate scientific achievements. The universe is dynamic in ways that extend far beneath its luminous surface. The light we see, the electromagnetic radiation that has been the basis of all astronomy, until very recently, comes from matter that is hot or energetic enough to radiate. Stars, gas clouds, accretion disks, the hot plasma of the early universe. But most of the mass in the universe does not radiate. Dark matter, if it exists in the form most physicists currently suspect, produces no light at all. Black holes, once they have finished accreting, are dark. Neutron stars that have cooled below a certain temperature are essentially invisible to our telescopes. The majority of what the universe contains has always been hidden from our electromagnetic eyes. Gravitational waves are sensitive to mass and motion, not to luminosity. They carry information about the dark universe, the universe of objects that neither emit nor reflect light in any quantity we can detect. In this sense, gravitational wave astronomy is not just an extension of existing astronomy. It is access to a previously hidden layer of reality. What that layer contains in its entirety, we do not yet know. The catalogue of gravitational wave detections is still young. The frequency bands accessible to current instruments cover only a narrow slice of the full gravitational wave spectrum. The sources we have detected so far, stellar mass black hole and neutron star mergers, are among the loudest signals available. The quieter signals, the continuous hum of asymmetric pulsars, the background of countless distant mergers, the primordial echoes of the Big Bang itself, are either at the edge of detectability or still beyond our reach. But the trajectory is clear. Each generation of detectors has been more sensitive than the last. Each new facility has extended the reach of observation. Each new frequency band that becomes accessible has revealed new populations of sources. The pace of discovery is accelerating, not slowing. Consider what the next few decades are likely to bring. The Einstein telescope and cosmic explorer, if built as planned, will detect neutron star mergers anywhere in the observable universe. They will build a catalogue of tens of thousands of events, large enough to trace the history of compact object formation from the present day back to the first stars. LISA will detect supermassive black hole mergers across the universe and provide exquisitely detailed maps of space-time around the most massive black holes we know of. Pulsar timing arrays will continue to refine their measurement of the gravitational wave background, potentially resolving it into individual sources and extracting information about the population of supermassive binaries in galactic centers across cosmic time. And beyond all of this, there is the possibility that the universe contains gravitational wave sources that we have not yet imagined. The history of astronomy is full of objects and phenomena that were discovered without prior theoretical prediction. Pulsars were not predicted before their discovery. Gamma-ray bursts were a complete surprise. Fast radio bursts remain only partially understood. The universe has a habit of containing things that we did not think to look for, and revealing them only when our instruments become sensitive enough to notice them. Gravitational wave astronomy is a young enough field that it is still in the phase of finding the things it expected to find. The predicted sources, binary black holes, binary neutron stars, mixed mergers, are being detected and catalogued. But as the sensitivity increases and the catalogue grows, the unexpected will begin to appear. Some detections will be difficult to classify. Some will have properties that do not fit existing models. Some may point toward phenomena that require entirely new physics to explain. The possibility that gravitational wave observations could reveal new physics, physics beyond the standard model of particle physics, beyond general relativity as currently formulated, is taken seriously by theorists. cosmic phase transitions, the dynamics of inflation, exotic compact objects made of hypothetical fields, all of these could leave imprints in the gravitational wave spectrum that would be visible to sufficiently sensitive detectors. Finding such an imprint would be transformative in a way that goes beyond even the remarkable achievements of the first decade of gravitational wave astronomy. It would tell us something about the fundamental laws of nature that no other observation could reveal. There is also the question of what gravitational wave astronomy will mean for our understanding of black holes specifically. Black holes are the most extreme objects general relativity predicts, and the theory makes very specific statements about what they can and cannot be. In general relativity, a black hole is completely described by just three numbers: its mass, its spin, and its electric charge. Everything else about its history, the star it formed from, the material it has accreted, the mergers it has undergone, is hidden behind the event horizon, inaccessible to any external observer. This is the black hole no-hair theorem, and it is one of the most remarkable results in theoretical physics. Gravitational wave observations of black hole mergers, and particularly the ring-down signal as the final black hole settles, are a direct test of this theorem. The ring-down consists of a superposition of damped oscillations called quasi-normal modes, and general relativity predicts exactly what frequencies and damping times these modes should have for a black hole of given mass and spin. If the no-hair theorem is correct, measuring two or more modes and checking their consistency should always give the same answer. If it is not correct, if black holes carry some additional structure that general relativity does not account for, the modes may not be consistent with each other. Current detections are not yet precise enough to perform this test rigorously. The ring-down signal is the quietest part of the gravitational wave event, arriving after the peak of the merger when the amplitude is already declining. But next-generation detectors, with their greatly improved sensitivity, will be able to measure multiple ring-down modes for many detected events, making it possible to test the no-hair theorem with real precision for the first time. If the theorem holds, we will have confirmed one of the deepest results in classical general relativity, using direct observations of black holes in their most dynamic state. If it fails, we will have discovered that black holes are more complicated than Einstein's theory describes, and we will need new physics to explain what they actually are. Either outcome advances our understanding. That is the nature of good science. The observations constrain the possibilities, and every constraint, whether it confirms a prediction or falsifies it, tells us something true about the universe. As we look forward to the decades ahead, it is worth remembering how recently all of this began. The first gravitational wave detection was less than 10 years ago. The field of gravitational wave astronomy is younger than many of the graduate students currently working in it. The instruments that will define the next era of discovery have not yet been built. The sources that will produce the most significant discoveries of the coming century have not yet been detected. We are at a moment analogous, in some ways, to the early days of optical astronomy, after Galileo first turned a telescope toward the sky. The instrument was new. The discoveries were immediate and transformative. The full implications took generations to unfold. What Galileo saw in 1609 eventually led, through centuries of observation and theory, to our modern understanding of the solar system, the galaxy, the expanding universe, and the Big Bang itself. The path from the first observation to the full scientific picture was long, and it passed through discoveries that no one in Galileo's time could have anticipated. We do not know where the path that began on September 14th, 2015 will ultimately lead. We do not know what the gravitational wave universe will look like when we can see all of it, at all frequencies, with instruments sensitive enough to detect the faintest signals. We do not know what surprises are waiting in the data that future detectors will collect. What we know is that a door has been opened. A new sense has been acquired. A channel of communication between the universe and human understanding, one that has existed since the first moments after the Big Bang, has finally been made accessible. Somewhere out there, black holes are merging. Neutron stars are colliding. The fabric of space-time is rippling with the echoes of the most violent events the universe can produce. Those ripples are traveling outward in every direction at the speed of light, passing through everything, carrying their messages faithfully across billions of light years of space and time. We are listening now, and the universe, it turns out, has been speaking all along.